Okay, so today we're gonna talk about a 2.3 flow through circular tube, and also 2.4 maybe if we have enough time about 2.4. And after that, I will give you an assignment for you to do it by yourself. So at least that will give you you can try it by yourself from an example of last year's or previous year's exam. Okay. All right, so now we're gonna talk about the flow of circular tube, but before that, let us uh, read the introduction about the phenomena. Wait, give me 1 second to close the door. Okay, so the flow of circular tube, or the flow inside the pipes, yeah. So the flow of in circular tubes is encountered frequently in physics, in chemistry, in biology, in the transport of water from the ground into the plants, yeah. So I remember before this we have Professor Mubiar almarhum, ya. Professor Mubiar Purwasasmita likes to explain about and also and he has a really good experience on the transfer phenomena in biological system, and he says that the capillary pembuluh capillary, yeah, the capillary from the plants, from the roots of plants, and then from those capillaries it actually follows the uh, transfer panel in momentum, yeah. Okay, and then at that time he developed a method to increase the momentum transport of the plants. In this case is for rice field, for the rice, and then he can get like very high productivity of the rice field. That's just one example. And also in physics, in chemistry, we also have a lot of explanation about for application about the circle tube. In chemical engineering, in many for example, for designing plants, chemical plants, for running every day to day chemical plants. Of course, we always encountered pipelines, okay, and then in those pipelines there are flow of fluids, okay. So in this case, we're gonna talk about the steady state laminar flow of fluid with a constant density and viscosity. Okay, so let me open the PPT. All right. So now we're gonna talk about the flow through circular tube. Okay. So we can. So first we will consider a steady state. Why it is a steady state? That is because we want them to be independent of the time. Okay, if you don't choose steady state, then later on the velocity or the momentum flux and all of the quantity that we're looking at, it would be a function of time. Okay, so we eliminate the function of time by considering it is a steady state. Okay, and again the second one, we have to also consider the fluid is a laminar flow and also should be a Newtonian fluid. Okay, um, why is so it should be Newtonian fluid. Newtonian fluid, that means it follows the Newton's law of viscosity, where is the mu equal the flux momentum equal to minus mu dv z over dx, for example. And then this one also, we also consider a constant density and viscosity, and then this is actually flowing downwards in a vertical tube with length of L and radius of R. Okay, so so let's say we have the pipes there. So we have the pipes. Okay, and then because of the pipe, so it is much is it the best for us to use a cylindrical coordinate. Okay, because the vertical tube has the length of R and also a radius of R. Okay, so then that we have to use cylindrical. Okay, now let's try to imagine about the phenomena where we have liquid and then it is falling downwards under the influence of a pressure difference and a gravity system. Okay, and the tube length is actually much larger compared to the tube radius, and then we didn't consider the N effect. Okay, so the N effect, the previous one and also the after the L, we neglected. Okay, now what can we postulate? Okay, so the first one we learned from the previous example about the fall of falling film. Usually the first we have to write first the coordinate. Okay, the coordinate, it should be cylinder, and then where we put the zero, the point zero, it should be at the center of the axis line of the cylinder. Okay, so this one, let's put it in the middle. The one that the flow should be in the z direction. Okay, and then the z direction, and the radius, that one, yeah, is in the r direction. Okay, in cylindrical coordinate we have a coordinate of r and then z and then theta, where theta is the circular the degree, this the circular one. Okay, so that means the phi z is so phi z is actually the one that pass this in these sides. Okay, this is phi z, and then phi r is the phi that pass that have direction to with respective of the r, and then phi theta would be the one that is swirling like this. Okay, remember, so the phi theta would be the one that rotates. Okay, in this case the fluid will fall downward under influence of pressure difference and gravity, so the fluid will be also just travel from the top to that one. Okay, so that means the phi would be only happen in the z direction. Okay, if the phi doesn't have the on the r direction. Okay, so what can we postulate? The first one is phi z. We have phi z, phi to the direction of z, and then it is actually a function of r. Okay, dia berubah terhadap r. Okay, so the phi z is a function of r. Kecepatan arah z itu berubah terhadap arah r. Okay, so why it is function of r? Because we know at the wall, because the wall is stationary, diam. Okay, we don't have the phi z. Okay, we don't have the velocity of the fluid. Remember from the last week's lecture, from Wednesday lecture, if we have if the solid is stationary, then the velocity of the fluid also stationary. Okay, equal to 0. In here, in the middle, there would be a lot, there would be Phi, and I think the Phi over here would be the maximum one because there is no resistance, nggak banyak tahanan. Okay, and then it's gonna be very, it become to zero again when it touches the wall. Okay, so we can postulate that V equal to Phi z, if Phi z equal to Phi z and a function of R. And the second one, do we have Phi R? Phi with the velocity with the direction of R?
No, ma'am.
No? Okay, good. Why, Christian?
Because the fluid is actually flowing downward, so there's actually no fluid in the direction of the R direction.
Right. Okay. So that's correct because the velocity is falling downwards. Okay. How about phi theta? Do we have phi theta?
No, Bu, it's also zero.
No, ma'am.
No. Yeah. If there is a phi theta, so that means the fluid will rotate. Okay. It will sometimes there would later on there would be an example as well where we have two cylinders and between the cylinder we put the fluid and then we rotate those cylinders, so the fluid will just rotates like that. So that in this case that we have phi theta, but in this case we only have phi z. Okay, so here we have so you should understand this one, and then so phi theta is equal to 0 again, and the pressure. Okay, so this one, the pipe is actually quite long pipes, and then it is a closed system. So you should you should know here for a closed system we do have a pressure difference. Okay, for closed system we do have a pressure difference with Z. Okay, so that would be pressure difference in C. Okay, so that means we have to know that on the closed system, like inside the pipe, this one, the P would be equal to P. We have the P or pressure, but it's a function of Z. Okay, this is actually contrary with the open system. I'll just write it here so you can remember. So in open system, P is the same in any direction, yeah, in any direction at that time. Okay, so when we look at here, so here from here we can see that the non-vanishing component of shear stress or for momentum flux here is tau rz, is actually or tau zr, which is minus mu dv over dr. Why? Because here we know that we have the velocity only function with r, so the tau that we have is tau rz, which is a function of minus the viscosity dv, the difference of velocity to z to the radius. Okay, so it is quite similar with the previous one, but first we have to change the coordinates, okay, and then be careful to again identify which are the non-vanishing velocity. Okay, so so the first one we identify. No, I think the first one should be. Okay, I'll write here. Determine the coordinate. Yeah. The second one we have to identify non-vanishing velocity. Okay. And the third one, sketch shell momentum balance. Okay, so you can imagine that here this is one cylinder, and then we cut it half. Okay, we cut the cylinder in half so we can know the thickness or the R that we're looking for. Okay, so this is actually the cylinder. So it's actually start with like this. Okay, and then we cut them in half. Okay, and after that we make the shell, the thin cylindrical shell. Okay, the thin cylindrical shell here is actually has a thickness of delta x, so delta r. Okay, so you can imagine that in your cylindrical pipe, you construct a thin shell, okay, a thin shell of this tube, okay, like this, okay. Let's say this is the tube, yeah, that one is the tube, okay, and this tube has length of L, okay, the length is L, okay, so this one the length is L, and then this one, the keliling, yeah, the length of this one is the 2VR, okay, and the thickness is very small, but the thickness is delta R. Okay, so we sketch this shell momentum balance. Okay, so this is check this shell momentum balance, and also we determine the coordinate, which is here the Z, and this is R. Okay, and after that, when we find the you have to sketch the shell momentum, and the fourth one is we have to develop shell momentum balance. Okay, so you can imagine here we have a CZZ when Z equal to 0, okay, which is flux momentum of Z momentum at Z equal to 0, minus CZZ at Z equal to L, which is flux momentum out at Z equal to L, and then here the momentum in, we're gonna start the momentum in from the highest velocity. Okay, we know the highest velocity should be in the middle, so we put the flux momentum inward from inwards to out, from inside of the shell to the outside of the shell. Okay, so this is also, there's a C RZ at R equal to R, and here also CRZ equal to CRZ at R plus delta R. Okay, so that and then let's try to sketch them. Looks like I need to maybe just add one more line there. Okay, so let's write the sketching, okay, the shell momentum balance. Okay, you can try write it also in your book, yeah, or in your pad or something. Okay, first let's consider we have CZZ at Z equal to 0, and then we have to multiply with the area with the cross section. Okay, so the area, maybe I'll write in this case here, so the area would be the circle, yeah, or the keliling, multiply with the thickness, or would be equal to 2VR. Let's say it's equal to 2VR because we put it into like that, and then multiply with delta R. This is the area of this CZZ, okay, this thin shell. How about the area of the inside? The area of the inside, that would be again the circular length, yeah, Lily, 2 VR, multiply with the length. Okay, multiply with the length, which is L. Okay, and for the area out would be 2V, but the R is not the R, but should be here would be R plus delta R. Okay, R plus delta R multiply with L. Okay, so again, the momentum balance means you have to multiply the momentum flux with the area that is perpendicular to the direction of the momentum. Okay, let me stop here, and then please let me know if you have any questions.
Ma'am, I have a few questions, ma'am.
Yeah.
Could you go back to the previous slide? Ma'am, so in point number 3, could you explain again what the end effect actually is?
Right. The end effect is maybe I can explain it like this. So if in end effect, if we have a very long tube, yeah, and then maybe in the beginning here there is I don't know, maybe an elbow or another disturbance, and around here also there's also disturbance. We don't consider that one. We only consider the one that the length is L. Okay, so we only consider in this case. Okay, the end effect is neglected. That means if you consider the in effect, sometimes there would be a disturbance at the bottom and also disturbance at the initial ones. Okay.
Okay, ma'am. Ma'am,
Yeah.
can I ask another question, ma'am?
Yes.
Sorry. How to differentiate which problem is a closed system and which one is an open system?
Right. To know the closed system, usually that should be it shouldn't the fluid should not contact with the gas or the atmospherics. Okay, so if your fluid has a contact with atmospheric pressure or a gas or the udara or the air, that can be considered an open system. But if in the system is only, for example, the pipe, the fluid inside the pipe is full, for example, it is a closed system. However, if, for example, I have this circular tube, yeah, and then I will pour some fluids, and then the fluid is falling outside this the cylinder, so the fluid has contact with air. Okay, so that would be an open system. Okay, but if I have all the fluid inside here, like quite long one, okay, and then it's just full, then it can be it is considered as closed system. All right.
Okay, ma'am. Thank you.
This is actually very crucial information because if we will not saying in the exam that okay, this is closed system, so you have to use this formula, or this is open system, you have to close this formula. No, we're not gonna say that. So it is part of the answer to identify which one is closed system and which one is open system. Okay, and I think the easiest answer to say in open system the fluid has a contact with air, and closed system the fluid is just really inside the container, yeah, the wall. Okay. Yeah. Any other question, please? This one or in the, this part?
Bu,
Yeah.
I don't understand why you have to relate it with the area, Bu.
Why you have to relate it with the area, right? Here's the thing. It's called the momentum balance. And the momentum balance is actually the flux momentum multiply with area. Okay, why? Because our C, yeah, CVV, that is actually a flux momentum flux. And momentum flux is actually rate of momentum, yeah, the rate of momentum of the fluid divided by area. So if you want to set up the momentum balance, then you have to multiply it with area.
Okay, I understand.
Yeah.
Thank you.
Okay. And then so you have to really consider the flux momentum and then which area that is perpendicular to that direction. Okay. Any other question, please?
Ma'am, I have a follow-up question, ma'am.
Yes.
So correct me if I'm wrong. So actually, the main purpose of the area is actually to what is it called? To actually erase the area denominator. Is that correct, ma'am?
Yeah. So any quantity with flux means the rate of something divided by the area. Okay. So if you want to have, for example, the mass balance, of course you want mass in minus mass out plus the mass accumulation. If you want to have a momentum balance, there should be momentum in minus momentum out plus the accumulation of something. Okay. And in here, the quantity that we have is momentum flux. Okay, so then we have to multiply it with the area.
I see, ma'am. Thank you.
Okay, anyone? Question?
I have another question.
Yes, Fatia.
From the previous slide though, to calculate the area in, shouldn't we times the circumference by 2, Ibu? Because there's 2 circles, right? From the at the top of the cylinder and the bottom.
Oh, yeah, because it is perkalian, yeah. So it's not additional. So this one, the cylinder, multiply with the L.
So
it's not additional, right?
But if there's 2 circles from the top and the bottom, shouldn't you also consider the both circles?
No, because you try to cut the cylinder and then make it like this, and then this one is 2 VR and this one is the L. Right?
Okay, I got it.
R and then this is R and this is L, yeah. So yeah, this is 2 VR and this is L. So if you imagine yeah, so it's only perkalian, yeah, a multiplication. Okay, but from the outer one, where is it? But from the outer one here, this one, from the outer one, the outer area is the keliling, yeah. The R is actually has R plus delta R for the radius. Okay, so this multiply with L. Okay. All right, so I don't know, do you want to write it out first?
Yes, it's all good now.
Okay, right. Okay, so let me erase this one. Let me. Okay. Yeah, wait. Okay. I think I have to add one more then. Okay, so let's try to do it by one. So I'm gonna maybe start sketching again. So let's sketch that one there. We have, this is R. This is the sketching. This is the shell. Okay. This is from here is R, and up to here is R plus delta R, and this is at z equal to 0, and this is z equal to L. Okay, so we can start first with here, which is C Z Z at Z equal to 0, and this is the outer one is C Z Z at Z equal to L. Okay, so we have C Z Z at Z equal to 0 multiply with the area. So what is the area here? Which is 2VR multiply with delta R. Okay, so 2VR here multiply with delta R, and then minus C Z Z at Z equal to L, multiply again with 2VR delta R. Okay, and then plus C R Z, this one, yeah, this one we have CRZ in, and there is CRZ at R plus delta R. Yeah, so we have CRZ at R multiply with 2VR multiply with L, okay, and then minus CRZ at R plus delta R, okay, multiply with 2V. It's actually R plus delta R, but then let me write this one, R plus delta R multiply with L. Okay, and then after that we also have the gravity. Okay, for gravity we will calculate it with rho and then multiply with the volume again. Okay, for the volume we will consider the thickness, the cincin, yeah, the area of the ring yang cincin di atas, this one, which is 2VR delta R multiply with the length. Okay, and then multiply with the G or the gravity to be equal to 0. Okay, so here you can maybe where is it? Okay, so if you go to the next one here, okay, here, yeah, so this is the in multiply with the area in, and then here the out multiply with the area out. You can see here that the area of the in would be equal to the out, yeah, because the same ring that we're looking for. However, when we talking about the area of CRZ at R, that would be different with this one, CRZ. Okay, but however, this one we can write it as R, but R at R equal to delta R. Okay, so let me check with the next one, next slide. Okay, so here the momentum in, okay, and this is the momentum out to VR delta R CZ at Z equal to L, and then this one is the momentum in. Okay, see the momentum out at surface R plus delta R is actually, we can write it as R, but at R plus delta R. Okay, and then we can also calculate the gravity force acting, which is rho multiply with the volume of the shell, of the cylindrical shell, and multiply with G. Okay, so now we're gonna end up with the momentum balance. So for the momentum balance, we can divide both sides with 2V delta R and L. Okay, why we didn't this one? This is because the R in here is not similar with R in here. Okay, so we can try to divide 2V, yeah, this should be divided with 2 delta R, and then get the limit would be equal to delta R equal to 0. Okay, and then let me give you the step by step so you can try to have a look. Maybe I can rewrite here, maybe different color. Okay, so we have divide them with 2 phi delta R and L. Okay, so here would be C Z Z equal to Z equal to 0 minus, now we still have the R, yeah, R. This is R C Z Z Z equal to L per L, because here we have to divide them with L, yeah, this one and this one, and then plus this one we have 2 phi RL, so then we have also R C R Z when R minus R C R Z at R plus delta R divided by delta R, and then plus we also derive this one, there become if we divide here, there is still R here, yeah, R rho G. Okay, now this one. Okay, so here and after that, so here you can have a look here. This is rho phi z z equal to 0 because we divide it to 2 phi R delta L, yeah, divided by L, and here we divide it also with delta R, that one, and this is R rho G or rho G R. I think maybe I'll just rewrite them with rho G with rho G R. Okay, now so, and then after that we divide the here, wait, for the R, oh, we have the yeah, okay, and after that we make it like this. We can rearrange them, so the CRZ, we make it into the limit, okay, into the limit. But if you think about it, the R in here is different with the R in here, so we have to put this inside the bracket. Okay, we have to put this inside the bracket because the R in here, this tells you about R plus delta R, while R in here is actually equal to R. Okay, of course there should be some arrangement, try to do it, so I really suggest you to do it in your own time, how to derive this into this equation. Okay, and here we have R CZZ equal to 0 minus R CZZ equal to L, and then the R is taken out, and also with the rho G, and then just rearrange the the condition, and then it would be like this. Okay, so and after that we have to evaluate the components of RZ and CZZ from the equation 171 and appendix B1. This is my writing from last year, but I think hopefully this still should be useful, yeah, for today. So first, for the tau RZ, again, it is based on the contribution of the shear stress. We don't have the pressure because I is not equal to J, so we don't have the pressure here. Okay, remember? And then rho phi R phi Z. Okay, but remember the phi R is equal to 0. Okay, because the phi R equal to 0, then you know that rho phi R phi Z is we can eliminate this one. Okay, and you can also eliminate this one, so then CRZ would be equal to tau RZ or equal to mu dv over dou R. So here is the one that we're looking for if you want to find the momentum flux distribution, or we can use this equation if we want to find the velocity profile distribution. Okay, and then the one over here, we also from yesterday, I think from on Wednesday, we know that it's CZZ equal to the pressure, okay, and then tau ZZ plus rho VZ VZ. Okay, P, we know the P, and then the P is a function of Z, so we don't eliminate the P, the pressure. Okay, and then minus this one, tau ZZ is minus rho dVz over dV, and then we know that there is no difference of velocity to the Z here, so it would be equal to 0. And then we have rho Vz Vz, but it's the same at Z equal to 0 and Z equal to L. Okay, so here, yeah, this is the what we know, yeah, the Vr equal to 0, Vz equal to Vz, function of R, and then we don't have V theta. Okay, and then so there is a pressure difference, like I said, because it is a closed system, and then there is no velocity gradient, so that will make this part is equal to 0. Right, now after that, again, the next step is to put the description of this C back into the momentum balance. Okay, so because maybe I should rewrite that one. Yeah, so this should this one. Okay, so let me try to rewrite. Maybe I can open the book so I can rewrite the for you. So I can rewrite that one for you. Okay. So first we have the limit delta R equal to 0 RC RZ at R plus delta R minus RC RZ at R, okay, divided by delta R, and then equal to C ZZ at Z equal to 0 minus C ZZ equal to Z plus L divided by L plus rho G R. Okay, that one there. Okay, now here this one we know that this becomes a different differential to respect to R of the R multiplied with tau RZ. Why? Because in the previous slides we know that tau RZ is equal to this one. Okay, so C RZ equal to tau RZ. Okay, and then put it back into the equation, then we got the this term would be equal to R tau RZ. Okay, got it? Okay, so this is the first one, and then the second one here for the pressure. Okay, for the pressure, if we look at over here, here we have the C that now become a pressure. Yeah, become the pressure. Okay, so become the pressure because this is 0 and this is 0, so C that become actually the pressure. Okay, and so the C that would be, I can write this part would be equal to P0 minus PL divided by L plus rho G R. Okay, and then they introduce, or we can write it would be like this, and then maybe put the G or the rho G, yeah, into this term. Okay, so P0 minus rho G0 like that. So this is actually just to make additional just convenient abbreviation, divide by L, multiply with R. So then it becomes the large or capital P, capital P 0, which is at Z equal to 0, minus capital P of L in Z equal to L. Okay, where the P, the large P, so let's introduce an abbreviation or new quantity, which is called the P, the large P. Okay, and this large P is actually convenient abbreviation for the sum of pressure and gravity term. Okay, and then so it's actually based on P, the P of the pressure, minus rho GZ. Okay, so that means when Z equal to 0, this term is 0. When Z equal to L, this term is L. Okay, this one, the term is L. Okay, so this convenient one. And then so then we end up with d over dr of r tau Z equal to P0 minus PL divided by L multiplied with R. Okay, this is now the differential equation of momentum flux. Okay, if you look at here, the R is inside the differentiation. Okay, because it always changing with the radius, and then there are large P or capital P, which is the convenient abbreviation of the sum, the pressure, the hydrostatic pressure of inside the pipe, and also the gravitational force. Okay, and this is divided by L because of the calculation, and then multiply with the R. Okay, and after that, the next steps to get the profile, we have to do the integration. Okay, and this is the integration, rho tau or Z. Yeah, just do the integration. So if I calculate the integration, that would be r tau rz equal to half of P0 minus PL divided by L multiplied with R squared plus C1. Okay, yeah, so this one I'll try to do the integration. R tau rz plus this is R, so when we do integration become half R squared. This is the constant, and plus the C1. Okay, and then we still have the term of R in here, so we have to divide both sides with R, and so that become this one, which is tau rz equal to this the constant, and then this R squared become R, and then C1 is become divided by R. Again, we have to find the boundary condition. Okay, so the next step is I think let me check the level of the shell momentum balance, and then maybe I'll write the number 5 is integrate the equation, and the number 6 is to find boundary condition. Okay, so the next one, we have to find boundary condition for this equation. Okay, so exactly the boundary condition that may be applied for the type of equation is actually so we evaluate with the following boundary condition. Okay, so where R equal to 0, because you remember the R is between R equal to 0 to R equal to capital R. So when R equal to 0, this value should be finite, harus ada. Okay, so tau RZ should be finite. So then that means the C1 must be 0. Okay, because if you have a number in C1, if you have this one a value divided by R, that become infinite. Okay, jadi tidak boleh ada C1. Yeah, so this one, so the constant C1 is evaluated by using the boundary condition, which is at R equal to 0, the tau RZ is finite. nilainya ada. Okay, so consequently C1 must be 0, for otherwise the momentum flux would be infinite at the axis of the tube. Okay, if we have number of C1, kalau kita punya angkanya, the momentum flux would be infinite at the axis of the tube. Okay, so now we have a C1 equal to 0, then we have the equation which is tau RZ equal to P0 minus PL per 2L divided by R. Okay, so this one is the RZ. So if I can draw the profile, if this is the, let's say, the circle tube, and this is, let's say, this is R and this is Z. The profile, if you look at here, so at the 0, at R equal to 0, the tau RZ would be equal to 0. Yeah, so at R equal to 0, tau RZ would be equal to 0. So this is, let's say, this is the 0. If R equal to R, so tau RZ would be P0 minus PL per 2L multiplied with R. So there would be a positive, both side is positive. So that would be, we can write it, it is a maximum in this case. So this tells you that the flux momentum would be 0 on the axis of the tube when R equal to 0, and the axis, so in the cylinder at the wall, the momentum flux would be the maximum, and then the maximum is, for example, in this case. And then if you look at here, the equation is linear, so it's gonna be increasing steadily in linear direction, right? Okay, so this is called the momentum flux distribution. Now I'm gonna stop here. If you have any question, please.
Ma'am, sorry, I have like a lot of questions. Sorry, this is kind of hard to digest. Could you go back to the previous slide, ma'am? Again, sorry. Again, ma'am. The one that you drew on previous. Okay. So I'm still kind of confused about how do you determine the denominator of the whole equation, ma'am?
So that's
so I mean, like, why is R not considered in the denominator?
Yeah, good question. We can consider the denominator where all of the value can be eliminated. Okay. Unfortunately, the R in here and the R in here is not the same. R-nya berbeda. Okay, because the R in here and in this case is difference, yeah, with the different value. This R here refers to R equal to small r, okay, which is this length. Okay, but however, this R over here is reversed to R plus delta R. Okay, so we can't divide them, we can't divide with R. Okay, so that's why here we can divide them with 2 phi, yeah, because all of the sides we have 2 phi, 2 phi, 2 phi, and 2 phi, so this can be implied, so we can just eliminate all of them. L, there is L over here, yeah, this is also the same, it's also L. This one doesn't have the L, but that's fine, we can just divide them with the L. And also delta R, and delta R over here, there is delta R in here, there is delta R in here, there's delta R in here, and because of that, and then usually we can divide them with delta R. It's actually what we were looking for, because we're gonna make a limit, and for the limit it should be divided with delta R. Okay, so it's a little bit tricky to find which one is the denominator. In one case, maybe you can just try to maybe just remember, dihafal, yeah. I don't know if the cylindrical coordinate, but it is quite typical. So in cylindrical coordinate, they won't divide them with R. because the R is a difference in this case. Usually for the tau RZ, the R is different. Okay. Hello? Yeah?
Oh, I see, ma'am. Thank you.
Yeah, okay. Okay, next question, please, from other people, please. Okay. Right. I got actually the a feedback, yeah, for your questionnaire from last semester, even different courses, but I'm also the lecturer, right? So, and then some of you suggest to me that you need to give problems. I need to give problems to you. So I have prepared one problem for you to try to do it by yourself, and that is a typical exam questions. Okay. So after this, maybe after 15 minutes, I will upload the like assignments in EduNext, and then please have a look, and then we can do some discussion. Okay, and for next week, how about what do you think about doing this offline? Is it better, or we should avoid it because the Omicron? What do you think? Do you prefer it online or offline? Hello?
To be honest, I'm not really sure.
Oh, you're not really sure? Okay. How about you, Dama? What do you think?
I'm a bit confused as well. I mean, like the experience of offline and learning more focused in class. I think that's one of the pros of offline class, but online class has recording.
Oh, okay.
So yeah, I'm a bit confused about that one.
Oh, okay. And the recording is useful?
Actually, yeah, I tend to like revisit recordings
Okay.
because I couldn't get the thing at first place.
Oh yeah, I know. Okay. How about you, Ayu? Do you prefer online or offline?
Halo Ibu,
Yeah.
my voice clear.
Yeah.
I have the same opinion as Dama, Bu.
Huh?
Hello.
Yeah.
Maybe my voice is a little bit gone, but I have the same opinion as Dama, Bu.
Oh, okay. So it is better to do it offline, online, because you have the recording. Is it?
Yeah, but offline makes me more
Is
focused.
it possible, Bu?
Yeah. Hello. Is it possible? What? Of course, the recording would be there because I think there should be Helena. Yeah, Helena is still overseas, isn't it? Hello. Yes, we still have recording while we have the offline class because the thing is the way we do the offline class, I will still open my I will still open the Zoom, and I will still menerangkan di Zoom. So I still be recorded, but the good thing with offline, there would be one by one approach to check which part that you're missing. I think that one is the one that sometimes you miss something, but the lecturer can't see that way, yeah, because we only get the result from the test, from the ujian, yeah, and after that, oh, you didn't pass, and then, oh my goodness, like that. Okay, but however, in the offline, we can identify which part is the understanding, and so on. Okay, I think the good thing also, like Christian asking a lot, that is really good, Christian, because okay, I know. Oh, okay, so the students actually need to be I have to emphasize about the area, for example. Oh, I have to emphasize about that one. Okay. Okay, but anyway, so actually I have you know, asked Pak Anggit to prepare the class, but because of this increasing Omicron things, yeah, and then have you heard about the PI Cirebon, yeah, which is one class have the COVID, yeah, do you know?
We heard already
Yeah, you
from
heard
listening to the
already.
induction yesterday.
So that is quite scary, yeah. So I think I suggest, or maybe here's the thing, or maybe let's make it on offline, online first, and then while try to do a booster vaccine. I just got my booster vaccine yesterday. Try to do a booster vaccine, and then we'll see with time. And then if you think when you do the exam module 1, for example, okay, it's just like much further than you think, and then we can try offline, okay. But now it's a little bit increasing, I don't know, it's a little bit bad, yeah. Okay, all right, okay. Now go back to this one here. So here in the exam, that I will ask, please, for example, I will ask the first one. I will ask, so for typical question here, first I will ask, determine the coordinate. Okay, so you have to be able to put the right coordinate, which is z over here, and then this is r, and then theta. Okay, if you put the coordinate over here or maybe somewhere around here, of course this is gonna be wrong. Okay, and then it's not itu syarat lulus, yeah. So you have to do the remedial. The second one, I will ask sketching the shell momentum balance. Okay, so you should be able to draw the sketching the better one, even in 2-dimension or 3-dimension. You can do it in 2-dimension or make it in 3-dimension, yeah, for any case. Okay, and then so this is also syarat lulus. And the next one, I will ask develop the shell momentum balance over this thin shell. Okay, and then this is what you should do. Write the momentum balance from momentum in to out, and then you divide it with the right denominator, like Christian said. Of course, it's going to be different between the Cartesian coordinate and the cylindrical coordinate. And after that, I will ask you to obtain the differential equation for flux momentum. Okay, and then this is the differential equation of flux momentum flux. Okay, and I will ask again the next part, so it is number 5, yeah. So the number 5, I will ask, do the integration of the momentum flux here with the appropriate boundary condition. So this is the number 6, yeah, to get the boundary condition. So you have to find the appropriate boundary condition. Okay, and then you will get the momentum flux distribution and also sketching the value. Okay, and after that, the next step is I will ask you to find the velocity distribution. So the number 7, I will ask you to develop velocity distribution. Okay, so I will ask velocity distribution, and how you're gonna do that is actually by applying the Newton's law of viscosity into the tau rz. Okay, so first you have the tau rz equal to P0 minus PL divided by L multiply with R. Okay, and then you change this with the mu, so minus mu dvz over dr equal to P0 minus PL divided by 2L multiplied with R, and then like that, and then here, and then after that, this is the differential equation, and after that you have to do the integration. Okay, so this is minus R, so with the integration this become R squared, and then this become 4. Okay, and then you have to find the C2. Okay, and the number 8, you have to find boundary condition related to boundary condition related to velocity. Okay, so if you think about it, what is the boundary condition related to the velocity? So let's sketch again. So this is the cylinder, and this is the flowing. Okay, so what is the boundary condition, kondisi batas related to the velocity? This is r equal to 0. This is r equal to r. Which value that the velocity that you have in this boundary condition? So which one? The hint is on the wall. Okay, anyone would like to try? Fatia, do you know what is the velocity on the wall?
Hold on.
Sorry? What
Wait,
is the
what was the question again, Ibu?
yeah, the question, what is the velocity of the fluid on the wall?
Would it be 0?
0. Okay, Kevin, what do you think? The velocity of the fluid on the wall? Kevin? Or Nadifa, what is the velocity on the wall? It may be right, 0 or not. What do you think? The velocity of the fluid on the wall. Hello, Nadifa. Aska. Okay, so Fatia says that the velocity on the wall, the inside wall, is 0. Do you agree? Anyone? Anyone? Would you agree? Christian, what do you think? The velocity on the wall equal to 0?
I think for now, I think it's 0.
Is it 0? Okay. Yeah. I'm actually, just to make sure, yeah, it's actually written in here. Yeah. So at r equal to r, the capital R on the wall, the phase z equal to 0. Why? Because when you have the fluid flowing, and then the fluid is on the wall, and the wall is stationary, diam. Okay, so the velocity of the fluid will be similar with the velocity of the solid. Okay, so if you have a stationary solid here, the surface, the solid surface, then the fluid also would be 0. Okay, so why? Because it has the highest restriction, or highest the shear stress in there. Okay, remember from here we know that it has the highest shear stress on the wall. So then it will have the 0. Okay, so here the constant is evaluated by the boundary condition. So the boundary condition that you have to find is the boundary condition with respect about the velocity. Don't find the boundary condition related to flux momentum, for example, but find the boundary condition related to velocity. Okay, and then this is r equal to r. Okay, so from here we find the C2, which is found at this one. So just make it 0. Yeah, so we can make it 0 equal to minus P0 minus PL for mu L R square plus C2. So we can get the C2 equal to that one. Okay, and then from this case, it is rearranged again into this one. So it's actually the phi z would be equal to minus P0 over PL divided by 4 mu L R square plus P0 minus PL divided by 4 mu L R square. Okay, and this one is rearranged into that part. Okay, so they taken out those you know, the constants there, and then make it like this. Okay, but this tells you that the velocity would be a maximum, which is equal to 1 multiplied with this quantity at the r equal to 0, or on the axis. Okay, so the axis would be maximum, and then on the wall this would be equal to r, so that become 1, so 1 minus 1 equal to 0, then the phi would be equal to 0. So if I can draw the the schematic of the profile, then it would be maximum around here, would be minimum around the wall, and it follow a quadratic equation, so it would be looks like this one. Okay, so it would be looks like that one. Okay, so this is called the velocity profile. Okay, so in a circular pipe, if you have the maximum velocity would be on the axis, and then the minimum velocity, of course, would be on the wall, which be equal to 0. And in contrast with that, the momentum flux would be 0 on the axis, and would be the maximum on the wall. Okay. So the implication, okay, so the maximum velocity would be at r equal to 0. Yeah, this one, the phi maximum. And then we can also calculate the average velocity, which is the integral of velocity to the cross section divided by the cross section. It is similar with the calculus, maybe, that you know. And then here it's actually equal to half of the phi z max. So if you can calculate the phi z max, then the average is usually half of the phi z max. Okay, it's different with the previous one with the falling film, which is around 2/3 of the phi max, but for the circle pipe is about 1/2. Okay, and then with this case as well, we can calculate the mass flow of the integration of velocity distribution to get the flow, that one there. And then the method is similar with the previous one, yeah, about the falling film, and also with the this one I think I have to delete it. It's not. I think I copy with the previous one. Okay, now, and then the force of the solid surface. Okay, for this, on the solid surface, on the inner wall, wait, okay, on the inner wall, that would be the force, which is the force is actually the momentum flux integrating the shear stress, and then with the area of the wall. Okay, so it is actually the momentum flux at r equal to r multiply with the area of the inner wall. Yeah, and then this is the area of inner wall, 2 phi rl, and then multiply with the momentum flux at r equal to r, on the wall, which is this one, and then we can derive this, and then that is the value. Okay, so this is the rho phi. So these are the force that on the solid surface caused by the shear stress on the fluid and solid surface. Right, so that is the end of the slide. So in one of the chapter of the exam module 1 about the momentum is about how to develop all these phenomena. It can be on Cartesian coordinate, it can be on a cylindrical coordinate. Okay, usually we don't include the spherical, yeah, coordinate bola. We don't that one there. All right. Now what I would like to do is to wait. I will close the screen. While do you need the uh, do you need my writing for the presentation? This presentation?
Probably.
Yeah, because after this, what I will do, I will give you an example. Yeah, I will give you example for assignment. So give me 1 minute, and then you can have a drink or something. Um, I'll try to upload this one. I have to let me wait. Okay, so I'm gonna download the PowerPoints and then I give it to you for additional topics. Yeah, there. And I will also I need to add the assignments as well. Okay, so let's have a break around 10 minutes. You can I don't know, maybe go to the toilet or to drink some water. Let's be back on 10:30 while I'm preparing the EduNext for the assignments.
Okay, ma'am.
Okay, everyone. I upload the notes, yeah, on the chat, so you can download it and also try to see it as well. And also you can open the on the EduNext. Maybe you can open on the course. Oops, not this one. Okay, you can open it on the course transfer phenomena, and it's on the introduction. Okay, is it? Where is it? uh, Wait. Did you find assignments?
I can't find it, Ibu.
Did you find it? Oh,
Not, it's not.
okay. So this is unpublished, so I need to check it and how to get the. Let's update it. Why this is what? Why you can't find it? Yeah, give me a second. There. Okay. Right. So I think I'll just give it without the assignments. I'll just give it to you, the chat, and then if one of your friends doesn't follow this for today's lecture, just ask me, and then I will give the assignments. Okay. Let's just do it manually. Um, okay. So I'll just put it again on the chat. All right. So Okay, I put it on the chat, so let's see those assignments and then have a look. And then for 15 minutes, try to figure it by yourself. And then the last 15 minutes, I will give some hints or answer your questions. Okay? Okay, so now you got the assignments and also the notes, right? Okay, so have a look. So rather than just listening, let's use this time to do exercise. Hey everyone, any questions regarding the assignments? Actually, what is the difference between this case with the previous one, with the cylindrical tube? Let's talk from the concept.
Maybe I'll like try to answer, man.
Yes, Christian.
So I think in this case, I think I don't know if it's correct or wrong. I think the momentum in the R direction is actually in the opposite direction.
The momentum in the what? In the
Yeah.
R direction?
It's actually opposite. It's like in a negative, sumbu negatif gitu, ma'am. I mean, I think probably.
Negative because of what? But it is similar, flowing downward, isn't it? Which one is negative?
I mean like the momentum, the R momentum, ma'am.
Oh, okay. The R momentum, I think the momentum to the R, it should be similar because it should be start with the highest velocity one to the lower velocity, and in this case, we know that this is air, yeah. Okay, so this is udara. Okay, so this is the inner wall of a vertical pipe, and it is wetted with flowing fluid. So the difference with this one is with the previous one. In the previous one, it is the inside of the wall, inside of the vertical pipe is fully filled with the fluid. Yeah, so it is a closed system. While in this case, you see that it is only wetted, hanya terbasahi, ada lapisan yang terbasahi. So it is a combination between the falling film, on Wednesday, the falling film of the liquid, and with this inside a cylindrical tube. Can you try to imagine that one? Yeah. So this is. Do you think is it an open system or a closed system?
Open system.
Yeah, it is open system because we have air over here. Okay, so because the water is not fully filled, yeah, the fluid is not filling all of this here, so but on the wetted area here, but it started from R equal to here into that one. So if you think about it, how about the shell balance? Yeah, the thin shell, is it similar with the previous one? It should be similar, but the difference later on, it would be the integration. Okay, so in the previous one, you do the integration from R equal to 0 to R equal to capital R, but in here, when you do the integration, you will start from this case, from this line, okay, or from R minus delta, let's say, okay, to the R. That would be one difference, yeah, that would be the that one for the area, the value for integration. The second one is actually I think from this case, and the second, of course, the first one is the difference is one is open system in here, but the previous one is the closed system. Okay, the second one is the border value, the value when we do the integration. Okay, so remember here we have to build the thin shell, and after that we have to do the integration, and then from the integration we can start from r minus delta to r, for example. Okay, sometimes if you can read the next part of in the book, they can also multiply, make this like a factor, for example equal to k r. So we do the integration from k r to r, so like a constant, maybe for example from k r a fraction to r, it can be also. Okay, and then I think the remaining should be the same, and the difference would be of course the mathematics, yeah, because the numbering is different, and then the mathematics, of course, maybe there would be some examples. So okay, so I really want you to try to do it by yourself. This is a typical question on the exam. And then I got it, this one from I think few years back of the exam. So first you have to remember here there are 5 steps, okay, and these 5 steps is actually usually it's the compulsory syarat lulus. Okay, so you have to determine the O cylindrical coordinate. For example, they should be around here, yeah, in the middle, in the axis. This is Z, and then write the shape and so on. And then sketch the fluid velocity profile. The fluid velocity profile, you know that it would be maximum on the the surface between the fluid and the air or the gas here, and would be 0 on the wall. Okay, so you can try to draw that. And then you have to sketch the cylindrical shell that will be used for the momentum balance, and then develop the shell momentum balance in steady state cylindrical shell, and then derive the momentum balance. So we have a shear force equation. Okay, so we have to find the flux momentum and also find the shear force equation. Okay, I'm sure all of these steps it should be mentioned in my lecture previously. I also have given the my hands out to you, my sketch and so on. So I guess try to do it by yourself, and then I'll try to figure out how to put assignment on EduNext. But if not, you can give it to me maybe through WhatsApp. Yeah, it's fine because only 8 people's here. Next time, yeah, on Wednesday. All right. Before we close the class, any question? Anyone?
Ma'am, I have a question.
Yes.
The first is regarding the assignment. So for number 1 to 3, is it possible if we use the figure and we can enter problems 1 to 3 on the same figure, ma'am?
Yeah, of course. But I think it is good. So you can print it out. You can print it out, or you do the sketching again, or it would be good if you can use different colors. Yeah. But if at least it can be, I can see it very clearly. Yeah.
And second, ma'am, so for next week's class, is it still going to be conducted online, ma'am?
For Wednesday, it's still online, but for next Friday, let's discuss it again on Wednesday. So we're gonna see about the Omicron or the COVID status. If in Bandung also increase significantly, then we have to do it online. But if still looks okay, and then the K3G tells it's still okay to do that one, and then let's do it on a Friday. But of course it is it's not compulsory. It is voluntary. So if you really want to have a session with me one by one, and then when we check again your your assignments, let's come to the campus so I can better explain to you. But if you can't do that, I'll make sure also that would be recorded. Okay. All right. Look. Any other question, please?
Ibu, I have another question.
Yes.
The difference between the open and closed system, is it also with the area of what we use, Ibu?
What area?
You know how in the previous closed system we discussed different areas like the inside area, the outside area.
Oh yeah, the inside and outside area. This is actually um, all of the if you write a shell balance. Let me open the book then. Maybe this one. Okay, so this area that I'm talking to you here is actually about the shell. Yeah, it doesn't really matter if you use closed system or open system. You still need to make a shell balance. Okay, so here, like in here, you have to make sure that this one, the outside of this, is actually the wall. Okay, got it, Fatia? Yeah,
Yes, Ibu.
yeah, this is the wall, but this one is the imaginary shell that we make in order to make the momentum, the momentum balance. Okay, I can give you example. For example, in the flowing fluids, there, okay, this one, it doesn't matter if even we have two plates, two plate, and then we fill it with fluids. Yeah, so it's a closed system or it is open system, we still need to make this shell thickness. Okay, so and if I can maybe explain to you like this, so this is the input, and then that would be the output, of course. Yeah, so it doesn't matter. Okay, but this is a open system because if you see here on the z-axis, or when x equal to 0, there is this is the gas or the atmospheric air, and this is the fluid. So this is an open system. Okay, but in this case, maybe let's open the circular tube there. This is a closed system because the pipe is fully filled with the water, with the fluids. Okay, so and then this is the imaginary one. Okay, for our assignments, this is the wall. Okay, but the fluid is only membasahi bagian dalamnya sedikit. Okay, so there's still room of the inside the pipe that is not filled with fluid, so it has a contact with the air. So the surface between the fluid and the air is considered the open system. Okay. Yeah.
Okay, Bu, I think I understand. Thank you, Bu.
Okay. All right, everyone. So thank you for your attention. I'll see you again next week.
Thank you very much, Ibu. Have a good day.